Welcome to Unsupervised Learning, finding patterns part of the fundamentals of machine learning course for aspiring AI practitioners. In this lesson, you'll discover how machines can identify hidden structures in data without any labels. Unlike supervised learning, where models learn from examples with known answers, unsupervised algorithms infer patterns solely from raw inputs. We'll explore techniques like clustering and dimensionality reduction, tools that group similar data points and compress large data sets, revealing unseen insights. By the end, you'll understand why unsupervised learning is crucial for many real-world applications. Unsupervised learning focuses on unlabeled data, aiming to uncover hidden relationships or groupings. Instead of predicting a target variable, these algorithms look for intrinsic structures. Think of it like navigating an unfamiliar city without a map. You rely on observations to find interesting landmarks or neighborhoods. This method is valuable in scenarios where labeling is expensive, time-consuming, or simply not feasible. From discovering new customer segments to spotting anomalies, unsupervised learning offers a fresh lens on complex data. Imagine an e-commerce startup puzzled by why some shoppers return every week while others just browse occasionally. Without explicit labels like loyal or casual, the team runs unsupervised clustering on purchase history, web clicks, and user profiles. Patterns emerge: groups of deal hunters, brand enthusiasts, and holiday-only shoppers. Armed with these insights, they tailor promotions to each group, boosting sales and satisfaction. This showcases how unsupervised methods illuminate hidden segments that standard analytics might miss. Clustering groups similar data points together, akin to sorting puzzle pieces by color or shape. Each cluster represents a natural grouping where members are relatively close to each other, while clusters themselves are farther apart. In market segmentation, for instance, different clusters might represent unique consumer behaviors. Recognizing these patterns guides more targeted strategies, whether it's personalized marketing or specialized product offers. Clustering helps teams see underlying structures that might otherwise remain hidden in a sea of data. A popular clustering algorithm is k-means. You choose k, the number of clusters, and place initial cluster centers randomly. Each data point is assigned to its nearest center, and then centers adjust to minimize overall distance. Through repeated iterations, distinct clusters form. K-means is fast and relatively easy to understand, but it assumes you already know how many clusters you want. Plus, it works best for data forming roughly spherical groups of similar density. Despite these quirks, it remains a go-to method for many clustering tasks. Hierarchical clustering doesn't need you to pre-specify the number of clusters. In agglomerative mode, it starts with each data point as its own cluster and merges them step by step. Divisive mode does the opposite, starting with all data as one cluster and splitting. The result is a dendrogram, a tree-like diagram revealing how clusters combine. By cutting the dendrogram at different heights, you can form various numbers of clusters. Though more computationally intensive for large data sets, its visual representation often provides deeper insights into data structure. Large data sets can have dozens or hundreds of features, making patterns impossible to visualize directly. Dimensionality reduction techniques compress high-dimensional data into fewer dimensions, like taking a lengthy article and extracting key paragraphs. This transformation preserves essential relationships while discarding noise, speeding up analysis and clustering. Although some nuance is lost, the payoff is a more manageable data set and clearer insights. Whether you're analyzing genetics or high-dimensional marketing data, dimensionality reduction often reveals hidden structures you'd never spot in the original feature space. Principal component analysis, PCA, is a classic dimensionality reduction approach. It identifies orthogonal directions, principal components, capturing the most variance in your data. By projecting onto these components, you can represent a dataset with fewer dimensions. For example, a 10-feature dataset might be mostly captured in just 2 or 3 principal components, aiding visualization and boosting algorithm performance. PCA also helps filter out noise, but interpreting the resulting components can be tricky since each is a mix of original features. While PCA works well for linear transformations, other methods like TS&E capture more complex, nonlinear structures. TS&E produces visually compelling 2D or 3D maps where similar points cluster closely. However, it can be computationally heavy and might distort global distances for the sake of revealing local structures. Beyond TS&E, methods like UMAP or autoencoders also reduce dimensions with varying pros and cons. Experimentation is key. Every dataset has unique quirks, so trying different approaches helps you uncover the best representation. Think of biomedical research involving thousands of genes measured across varied cell samples. A massive unlabeled dataset. Clustering gene expression patterns can group genes with similar behaviors, while PCA or TS&E helps visualize these patterns in just a few dimensions. Scientists might discover clusters of genes active in specific diseases. By focusing lab work on these high-potential clusters, breakthroughs happen faster. This scenario shows how unsupervised learning can guide researchers toward meaningful targets. No labels required. For practical hands-on experience, sites like Kaggle and the UCI Machine Learning Repository offer unlabeled or minimally labeled datasets perfect for unsupervised exploration. You could cluster country indicators to find geopolitical groupings or compress a large image dataset to reveal hidden patterns. These communities often include forums for sharing code and insights, helping you learn best practices. Always remember to review data usage policies and privacy constraints, especially for real-world projects involving sensitive information. Consider a financial institution processing thousands of transactions daily, most legitimate, some fraudulent. Without labeled examples of fraud, analysts apply anomaly detection, a form of unsupervised learning, to cluster transactions and highlight outliers. Suspicious purchases appear as distant points from the main cluster, maybe unusual times, large sums, or abnormal locations. Investigators then focus on the most deviant transactions. By narrowing the search, the bank saves time and spots potential fraud before it escalates. Unsupervised learning outcomes demand careful interpretation. Clusters or patterns can look neat, but may not always map to meaningful real-world categories. Domain experts often validate whether discovered structures are relevant or random. Choosing parameters like the number of clusters or dimension count can be tricky without labels for guidance. Analysts rely on metrics like silhouette scores or Davies-Bouldin indices to gauge cluster quality. A combination of algorithm experimentation and real-world context helps ensure you're unveiling genuine insights, not just noise. Throughout this lesson, we explored how unsupervised learning uncovers hidden patterns in unlabeled data, grouping points via clustering or revealing complex structures through dimensionality reduction. We looked at methods like K-means and hierarchical clustering, plus PCA and TS&E for dimension reduction tasks. Real-life examples, from e-commerce segmentation to gene expression, show how these techniques transform raw data into actionable insights. By combining algorithm experimentation with domain expertise, you can discover the unseen opportunities that might otherwise stay buried in your datasets. Unsupervised learning offers a versatile way to discover insights, from pinpointing new customer segments to detecting anomalies in finance or research. By learning patterns without labels, you're free to find unexpected groupings or reduce complex data into more manageable forms. These insights fuel innovation, cut down analysis time, and spark new ideas. With these unsupervised methods in your AI toolkit, you're better equipped to handle problems where labels don't exist or can't be easily obtained. Congratulations on completing this lesson, and we'll see you in the next module.